Hello, my name is Shahriari, and this is a lecture on linear algebra based on my book Retrolinear. The topic of this lecture is linear combinations and spanning. Let's think about the following scenario. You walk into a vector space. This is a vector space you're not familiar with. You introduce yourself. You try to get to know what's around you. You know that there are elements in this vector space. You know that there's an addition and scalar multiplication since this is a vector space, but you don't know what those operations are. You don't know what the elements are. You just know they exist. You look around and you found three vectors that you really like, v1, v2, and v3. So you like these vectors. What you want to do is you want to say, I want to create a subspace that contains these three elements. Of course, you could say, well, let me take the whole vector space V. That is a subspace and it certainly contains v1, v2, and v3, but that would be sort of boring. That would be a trivial way of creating a subspace that contains v1, v2, and v3. You want to be a lot more efficient than that, and you want to not include in your subspace any unnecessary elements. You want to only put in that subspace the things that you need. Constructing subspaces is important because the way we like to understand vector spaces is by their substructures, by their subspaces, and the way they fit together. So how would you do that? Well, first of all, you want to ask what elements need to be in this subspace, which we are calling W. W is the subspace that you're going to construct that is going to include v1, v2, and v3, and possibly other vectors. Well, for one thing, it will have to include the zero vector. Every subspace will have to zero vector. So you say zero vector, let's look around where that is. You bring that to the collection, to the party, and you say, you've got to be here with us if you're going to make a subspace. But you need to know more than that. You also need scalar multiples of v1, v2, and v3. You need things like 4v1 and 7v2 because the subspace is supposed to be closed under scalar multiplication. So since v1 is there, 4v1 will have to be there. Since v2 is there, 7v2 will have to be there, and 56v3 and so forth. But you need more than that. You need also closure under addition. Since these two guys are in there, 4v1 and 7v2, their sum 4v1 plus 7v2 got to be there, and things like 4v1 plus 7v2 plus square root of 3 minus square root of 2 times v3 got to be in this subspace also. Square root of 3 minus square root of 2 is just as good a scalar as any other scalar. So in other words, you will have to have all elements of this form, a scalar times v1, scalar times v2, and a scalar times v3 all added together. All those elements will have to be in W. The things of the form alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. And in fact, if you say that, then you might ask, well, do I need anything else? And the answer is, the short answer is no. If you just take all of these guys, then you've made yourself a subspace, and we'll make that clear in a few slides. I just want to say that if you do say that I'm going to collect from the vector space every element that is of the form alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, you don't even have to say that you need to add in the zero vector, because the zero vector is also of this form. It's 0 v1 plus 0 v2 plus 0 v3. You also don't have to say that this subspace will include v1, v2, and v3, because it automatically will. If you pick alpha 1 to be 1 and alpha 2 and alpha 3 to be both 0, then you will get v1. If you put alpha 1 and alpha 2 equals 0 and alpha 3 equal to 1, you will automatically get v3. So v1, v2, v3, 0 vector, and plenty of other vectors are of this form of a scalar times v1 plus scalar times v2 is scalar times v3. So let's make a definition. Those kinds of vectors are called linear combinations. The setup is that we have a vector space over R. Remember that when we say over R, we mean that the scalars are real numbers, and you have maybe a whole bunch of elements of V. Then any element of the form lambda 1 v1 plus lambda 2 v2 plus lambda n vn, where the lambdas are scalars, they're real numbers, is called a linear combination of v1 through vn. You have to find linear combination of a bunch of elements, and you do that by multiplying each of them by scalar, possibly 1, possibly 0, possibly something else, and then adding them together. One thing I want to say is that we didn't really have to have the scalars be real numbers. The same definition would work over any field. Scalars in a vector space don't have to be real numbers. They could be elements of a field. If this is your first time through linear algebra, you can just basically ignore that. And whenever you hear the field F, think of the real numbers, and there will be a lot of content in the stuff you will learn. But if you are interested in a more general situation, you will want to do things over a general field F, a place where you can add, subtract, multiply and divide by non-zero elements. Here's an example of using those vocabulary. We're learning this language, we're making words, and we need to learn how to use them. So we start with a vector space. This time the vector space is the vector space of 2 by 3 matrices with real entries. Again, we'll say over R. That means that the entries are coming from R. And here are three vectors, V1, V2, and V3. I'm calling them vectors even though they're matrices. They are matrices, they're 2 by 3 matrices. But this vector space is made up of 2 by 3 matrices. What's a vector? A vector is an element of a vector space. And because that's a vector space, these guys are also vectors. These are all elements of V. The question that I might ask is that, is V3 a linear combination of V1 and V2? That would be an appropriate question to ask. What am I asking? I'm asking, does there exist real numbers alpha 1 and alpha 2 with the property that V3 is alpha 1 V1 plus alpha 2 V2? Alpha 1 V1 plus alpha 2 V2 is a linear combination of V1 and V2. And I want to find out, is there one of those that will equal V3? So are there specific numbers alpha and alpha 2, alpha 1 and alpha 2 that will make alpha 1 V1 plus alpha 2 V2 be equal to V? There may exist, there may not. If they're not, then we say that V3 is not a linear combination of V1 and V2. If I can find alpha 1 and alpha 2, then I will say V3 is a linear combination of V1 and V2. How would I do that? I don't know what alpha 1 and alpha 2 are. I have to find those. Those are the unknowns. But I do know what V3, V1, and V2 are, and therefore I can substitute those in this equation and then solve for alpha 1 and alpha 2. Instead of V3, I put what it is, minus 3, 17, 0, 0, minus 10, 15. And the same with V1 and V2. Alpha 1 and alpha 2 I kept because I don't know what they are. Then I can multiply these into the matrices. I know how to do scalar multiplication. Alpha 1 gets multiplied inside, alpha 2 gets multiplied inside, and I know how to add the matrices also. After all, I am in this vector space, 2 by 3 matrices. I know how to multiply by scalars and how to add. If I do that, this is what I get. And I want this matrix to be equal to the matrix that's V3. So that means that entry by entry, they have to match. Now what we have is 4 equations and 2 unknowns. 4, not 6, because 2 of the equations are just 0 equals 0 that are automatically satisfied. What I have to do now is try to solve the system. The system may have a solution, may not. 4 equations and 2 unknowns, and it's quite possible that it doesn't have any solutions. Or it could have solutions. If it doesn't have any solutions, then I know that V3 is not a linear combination of V1 and V2. If I can find a solution, then it is. I'm not going to solve this in public. Some things are better done in the privacy of your home. How would you do that? You would use the method from the 9 chapters, what's known as Gauss-Jordan elimination. In linear algebra, almost every problem tends to end at solving a system of linear equations. And for that reason, we like to have a systematic way of solving systems of linear equations, and we use Gauss-Jordan elimination, or as I like to call it, the method from the 9 chapters. And if you do that here, and again, you can do that yourself, you get that alpha 1 is 4 and alpha 2 is 7. So I did find a specific alpha 1 and alpha 2 that work. If you don't believe me, you don't have to solve that. You can just check that if you multiply V1 by 4 and V2 by 7 and add them, you do get V3. So V3 is 4V1 plus 7V2. And as a result, I know that V3 is a linear combination of V1 and V2. I'm not interested in just one linear combination. I want all linear combinations of a bunch of elements because that's how I'm going to make a subspace. And so for that, we're going to introduce a new name. We mathematicians like to define new concepts and names. Some of that is because then that makes it very precise. We will know exactly what we're talking about, and we can slowly figure out, build intuition for that notion and learn how to deal with that word. So span, what is a span? What's the setup? We have a vector space. You have a non-empty subset of V, so these are your favorite elements. And then you look at all linear combinations of elements of S. So you take elements in S, S is a set, look at all the linear combinations, multiply by scalars and add them. Everything you can find, you put in this set and you call it span of S. Now, if W is the span of S, some of the ways that we use this vocabulary is we say that S spans V. Oops, S spans W, not V, sorry. And W spanned or generated by S. That is a typo. Those V's should be W. This definition is almost right. It's not 100% correct though. I need to fix something before it actually becomes correct. And that's, I have to add a number finite. I also have to change those V's to W's. but I mean, that's actually pretty important to do, because I had a V before, and this V is not, the second V and the third V should really be W. If W is the span of S, we say that S spans W, not V, and W is spanned or generated by S. But what's that thing about finite about? If your set S has a finite number of elements, if it has 3 elements, 5 elements, 3 trillion elements, it doesn't really make any difference. You find all linear combinations. But if your set S has infinite number of elements, then you might be tempted to find an infinite linear combination, and that's not allowed. Even if you have infinite number of things in your set S, you have to take a finite number of them. You have to choose some of them, a finite number of them, and then find linear combinations. So only find linear combinations of a finite number of things. Never find a linear combination of infinite number of things in linear algebra. So here's an example to make that little point, that little red herring clear. So PR is the vector space of all polynomials with real coefficients, not polynomials of with some bound on their degree, just all of them. And in that situation, I'm going to let S be this infinite set that consists of even powers of x, x to the 0, x squared, x to the 4th, x to the 6th, and so on. So this is an infinite set. And if I ask, well, is 5x squared minus 3x to the 6 plus x to the 48 in the span of S? And the answer is yes, because you use the elements of those elements, multiply them by constants, and add to them. That's a linear combination of elements of S, and so it's the span. Something like 3x squared plus 7x to the 47th is not, because x to the 47th is not there, and so you don't have those things to create 3x squared plus 7x to the 47th. But more importantly, x squared plus x to the 4th plus x to the 6th plus going forever, the power series is also not in the span. That's a legitimate thing to study, but it's not a part of linear algebra and studying span of S. Because if you find span of S, you have to pick a finite number of elements of S. Okay, let's look at another example. This time my V is the 2 by 2 matrices with real coefficients, M2 to R. And here I have two elements, a set with 2 elements, 2 vectors, mind you, or 2 by 2 matrices. One of them is 1, 1, 1, 0. The other one is 0, 0, 1, 1. And I'm going to ask, what's the span of S? Well, the span of S is all the linear combinations of these 2 elements, the set of all linear combinations. I don't have to say finite linear combinations, because there was only 2 things. All linear combinations are finite. If there was infinite number of things, then I would have to make sure that you understand that when I say linear combinations, I'm only going to take a finite number. And so the span of S means you multiply the first matrix by alpha, the second one by beta, and add them. And anything you get like that is the span of S, and those are the only thing that are in the span of S. And if you know how to multiply by matrices by constants and add them, and if you do that, then what you get here is the following types of matrices. So any matrix of this form, any matrix of the form alpha, alpha, alpha plus beta, beta is in the span. So for example, if you take alpha to be 47 and beta to be 47, you get that 47, 47, 94, 47 is an element of span of S. On the other hand, a matrix of the form or a vector of the form 1, 1, 2, 2 is not in the span, because here alpha is trying to be 1, beta is trying to be 2, but then the 2, 1 entry, the entry in row 2, column 1, it should be a 3, not a 2, and that's something that's not in the span of S. So span of S is those elements. Okay, now we want to state and then argue and give a proof of this theorem, the span theorem, the theorem that tells us about span. Why is it that we're interested in the span? So what is span? You start with a set, you make this span. You have a vector space, you have a non-empty subset of it, and then you can create the span, which is another set made up of linear combinations of elements of S, finite number of linear elements of S, and then you want to know, well, what is this span, this set? Well, here's some of the things you can say. The first thing, very important one, is that span is actually a subspace, and this is actually our go-to method for creating and constructing subspaces. So if you, as we said at the beginning of the hour, if you have V1, V2, V3, and V4, and you want a subspace that contains them, just find their span, all their linear combinations. That will be a subspace. The second thing is that if S, the set that you're going to find its span, already lies within a subspace. So if S is inside W and W is a subspace of V, then when you find the span, it stays within W. If S is in W, so will the span of S. So that's the second property. And the third one, which is actually sort of a reiteration, is the same as the second one. This is the first and the second one, is that the span of S is the smallest subspace of V that contains S. And I'll make clear what I mean by the smallest. What that means is that it's contained is inside every subspace that contains S. So if you want a subspace that contains S and you want to be efficient, not have extra elements, span is your answer. The fourth one is just a sort of almost a straightforward thing, that if you have S and you have a T and S is inside T, if you make S a little larger, add some elements and make it into T, then the span of S will be also inside span of T. And the fifth one is just specializing the span to one element. What if your S just has one element V? So you want to find the span of S just one element, then all you get is scalar multiples of that. That's just the definition, basically, really nothing to it. But let's see some of these things, what some of the arguments are. But before I do that, again, I stated this over R, over when the scalars are R, but this is really true about any field, as are almost every theorem that we prove in this class, that you could have the scalars be any field. The only difference here would be in the last statement, when you were finding the scalar multiples of that vector V, you will find them, the scalars just going to come from F. And in fact, in all of them, when you're finding linear combinations, the scalars will come from F. Okay, so let's now try to prove this. So the first statement was that, and maybe the most important one, is that the span is a subspace. How do I prove that the span is a subspace? Well, span is linear combinations of elements of S, so it's sitting inside the vector space V. And is using the same addition and scalar multiplication as V. So what I have to do to show that it's a subspace is I have to show that the zero vector is there, I have to show that it's closed under addition, and I have to show that it's closed under scalar multiplication. Now the zero vector is certainly there. Why? Because S is non-empty, so it has some element, little s, in there, and I can use the scalar zero. If you take the scalar zero and multiply it by any vector, you get the zero vector. And because so the zero vector is a linear combination of even that one element. Even if S had one element, zero would be in there. Now, to show closure under addition, I have to take two elements of S and show that their sum is also in take two elements in the span of S and show that their sum is also in the span of S. That's how I would show that span of S is closed under addition. So the two elements are going to be a linear combination of elements of S. And so maybe V1 will be alpha 1 S1 all the way to alpha n Sn, and the same with W. And this is where S1 through Sn are elements of S, and the alphas and the betas are scalars. Now, it might be that V and W aren't actually linear combinations of the same elements. Maybe V is just a linear combination of S1 and S2, and W is a linear combination of S2 and S3 and S4. But even so, we can write it like this, because for the elements that we're not using, we can always just put zero. And in fact, even if S was an infinite set, both V and W would be linear combinations of a finite number of things. And so by appropriately adding zero scalars, we could make both of them be linear combinations, maybe slightly fake ones, of the same set of elements, in the sense that some of those scalars might be zero. Okay, so what do I want to do? I want to add these, and if you add them, you can combine the like terms, and you will see that what you get is also a linear combination of those same elements, because alpha 1 plus beta 1, for example, is a scalar also. And so V plus W is in the span of S, and the span is closed under addition. And scalar multiplication will be a similar kind of an argument. So we do have that the span is a subspace of V. Now let's look at the other things that the theorem asked us to do. So one of them was the following question. If S is already inside a subspace of V, then the span of S is also in that subspace. So if S is in W, the span of S is in W. Now note that S could be just one or two elements, but span is a lot of things. But even though you're blowing up S and making it into span by adding all kinds of elements, all the linear combinations, you're not going to get out of that subspace. So why is that? Well, one way, let's think of it a little bit like have an image. So let's say V is this sort of big vector space, and W is some subspace of it. And S is sitting inside that. S is actually usually a tiny set of things. And what this says is that when you find the span is not going to go outside of W. So why is that? Well, elements of S are in W. I mean, that's what S being in W means. And W is a subspace, so it's closed under addition and scalar multiplication. So that means that if you take elements of W and add them, or multiplying by scalars, or multiplying by scalars and add them, you stay within W. And elements of S are in W, so when you're trying to find the span, which is finding multiplying elements of S by scalars and adding them, you are multiplying elements of W and adding them by scalars and adding them, and so you will stay within W, because W is a subspace. So the span will be in W, and that was the proof of that second statement. Now let's go to the third statement. That one was about being the smallest. Why is the span of S the smallest subspace of V that contains S? Well, I haven't quite 100% told you what I mean by smallest. It's not like vector, we can count the number of elements. They all could be infinite, but I mean something very specific. So again, what the picture we're thinking of is that we have V, and then we have the set S, and then we have the span, and we're saying that if you take, so we're saying the span is a subspace of V. Well, we proved that a span is a subspace of V, but why is it smallest? Well, it's because if another subspace W contains S, so if this is a other subspace that's coming through the door and saying, well, no, I am the one that you should be looking at, not span of S. Maybe I'm even smaller, or I've got some other advantages over span of S. If W is any subspace that contains S, we just showed that span of S is inside W. So span of S is in there. It could be all of W, but it can't be any bigger. So that's the sense we mean that span of S is the smallest. It's contained in every single subspace that contains S. If you're going to be a subspace, if you're going to contain S, you've got to contain span of S. And that's the notion of smallest that we mean, that something that's contained within every other one that has that property. Okay, the last two conditions are pretty straightforward. If S is, if T is slightly bigger than S, or the same size as, I mean, it has elements of S, but it maybe have some more things, then any linear combinations of S are also linear combinations of T, because elements of S are in T. So if I give you a linear combination of some elements S, you will say, okay, well, I want to think of this as a linear combination of elements of T. And therefore, span of S is everything that was a linear combination of elements of S is among things that are linear combinations of a T. I mean, T might have other elements, and so you can get things in the span of T that you couldn't in span of S, but everything in span of S is already in span of T. And if S has just one element, then the only linear combinations are of the form alpha V, where alpha is a scalar, and that's what that was. So there we go with the proof. So I'm going to now give you 3 examples and a little bit of a discussion. Well, the third one is a little bit of a discussion, and then we'll be done. So W this time is made up of 4 tuples. There's lots of symbols there, but if you look at that typical element in the curly brackets, it's made up of 4 entries. 4A, that's one thing, a number, because A, B, and C are real numbers, it says. And then 7A minus 2B plus C, that's another number. B minus C is a third number, and 3A plus 5C is a fourth number. And the question that I might have is, is W a subspace of R4? These are a bunch of elements in W. Do they form a subspace of R4? This seems a little bit off from our current discussion, but it's related, as you should see in a second. To answer this question, I have so far two methods. I could just go say, being a subspace, being a vector space, just go check every axiom of a vector space. Or I could be a little bit more clever and say, no, these elements are all sitting in R4 and they're using the same addition and scalar multiplication as R4. That's implied in this question. And therefore, I don't have to check most of those axioms. All I have to check is that, is the zero vector in here? Is it closed under addition? Is it closed under scalar multiplication? But now we want to come up with a third method for deciding whether something is a subspace or not. So I'm going to create some elements in W. So one thing I'm going to do is I'm going to let A be 1 and B and C be 0. That's one way to make one of the simplest elements that you can create in W. And then you get 4, 7, 0, 3. I wrote it as a row vector because I don't want to take too much room in my slides, but that T means transpose. And if you remember what transpose means, it means that you take every row and make it into a column. So 4, 7, 0, 3 transpose is the column vector 4, 7, 0, 3. So that W1 is an element of this W because I just found it. And I do the same thing with B. I let B be equal 1 and A and C be 0, and I get another element. And I put C equals 1 and A and B equal to 0, and I get a third element. So now I found 3 elements, W1, W2, and W3. And I look at the set consisting of these 3 elements. And then I ask myself, what is the span of these 3 elements? And it'll become clear in a second why I'm asking that. So I found myself 3 elements in W, and I can ask myself, what's the span of S? Now, so that means elements of the form AW1 plus BW2 plus CW3. And they are going to be of the form A times this column vector, that B times that second one, and C times that. And if you combine this, you will get the typical element of W. So by finding linear combinations of W1, W2, W3, you can get everything in W. And in fact, you only get elements of W. The span of S is exactly W. And so W is the span of S. So what? But now, we know that W is a subspace. Why? Because span is always a subspace. So this is sort of maybe the easiest, least calculation way of deciding if something is a subspace, by deciding that it is the span of a set of vectors. If you can find by hook or crook a set of vectors and show that whatever you were looking at is the span of those, then you know that it's a subspace. Now, the trick here is that, the downside is that you have to figure out how to come up with W1, W2, W3. Often, if there are parameters, like here A, B, and C, this trick of letting one of the parameters be 1 and the other one 0, and doing that for all the parameters works. But sometimes you might have to do something else. So there was one example that shows this span can help you decide if something, not only helps you create subspaces, can help you decide if something is a subspace or not. Here's another example by which I want to point out another technique. I have a set here S that has 3 elements in it. This time the vector space is polynomials of degree less than or equal to 2. These 3 elements are x plus 1, x minus 1, and x squared plus x plus 1. X squared plus x plus 1 is one vector in this vector space. Remember, vector spaces, their elements are vectors. So each one of these is a polynomial, but it's also a vector. One vector, x squared plus x plus 1 is one vector. X minus 1 is one vector. X plus 1 is one vector. So S has 3 vectors in it of polynomials of degree less than or equal to 2. And I'm looking at this and I'm asking myself the following question. Is the span of S possibly all of P2R? And maybe I suspect that that's the case. I'm suspecting that if I find the linear combinations of these, I can find everything in P2R. And I want to know, how would I prove that? Well, I might say, well, you have to take a typical polynomial of degree 2 or less, a plus bx plus cx squared, and see how you write it as a linear combination of these. That would work. It would be somewhat tedious. So instead, I'm going to try something else. We already know that span of S is in P2R. Span is a subspace of the big vector space. So it's already a subspace of P2R. The question is that, can I get every element of P2R as a linear combination of elements of S? That's what I'm wondering. And instead of worrying about every element of P2R, I'm going to actually try some very special elements of P2R first, just to get my hands dirty. So first of all, polynomial 1. I mean, that's a polynomial 1. Is that a linear combination of these guys? And you notice that if you take x plus 1 minus x minus 1, you will get 2. And so if you divide those by 2, you will get 1. So 1/2 x plus 1 minus 1/2 x minus 1, that's a linear combination of elements of S. So that means that 1, the polynomial 1, is in the span of S. By doing the same thing but adding, you will see that x is also in the span of S. And now I want to know, is x squared in the span of S or not? And what I have is that, well, what I noticed is that x squared is x squared plus x plus 1 minus x minus 1. It's a linear combination, but x and 1 are not in S actually. But x and 1 are in the span of S. We just found that x is 1/2 x plus 1 plus 1/2 x minus 1, and 1 is 1/2 x plus 1 minus 1/2 x minus 1. So if I put, instead of x and 1, these linear combinations that I already found and combine like terms, I will get that x squared is a linear combination of those 3 elements. That first element, x squared plus x plus 1, is in there, and the other guys are also in there. And so now I know that that's also in the span of S. So what? I just found 3 elements. P2R has infinite number of elements. I'm not nowhere near done, but I'm almost done. In fact, I actually am done. Why? Well, all I just found out was that 1x and x squared is in the span of S. Span of S is a subspace, and these 3 elements are in it. But what we proved in our span theorem was that if something is in a vector subspace, its whole space, its whole span will also be in that subspace. In this case, the subspace is span of S, and the set is 1x and x squared. That set, 1x, x squared, is in this subspace span of S, so the whole span of 1x, x squared is going to be in the span of S as well. And what is the span of 1x, x squared? That's all of P2R. So all of P2R is in the span of S. We had originally in the second line said the span of S is also a subset of P2R. Because we have both inclusions, we conclude that the span of S is P2R with very little calculation involving A's, B's, and C's. Just by showing that 1x and x squared are in the span, we showed that everything is. So the moral of this story is that if you, instead of showing that every element of a vector space or subspace is in the span, all you have to do is show that a set that spans that thing, those elements are in there. 1x and x squared were special because together they spanned all of P2R. Okay, my final slide is about vocabulary and how we use it. And mathematics is very precise language. It's one that not quite like English. So you don't have as much freedom as in English. And I want to point some of that out because this is some common mistakes. So W, let's say, is a bunch of vectors in R3, the ones of the form A plus B, and B. W is a subspace. You can actually find it the same way we did in an earlier slide by finding a set that spans it. So here's my first question. If I want a set S that such that span of S is W, a set that spans W, the set that when I find their linear combinations I get W, can I use the following phrase? Can I say, or the following sentence, find the span of W? Well, I want a set that spans W, so find the span of W. The answer to that is no. That's just the wrong way of using this word span. You want to say you want to find a set that spans W. You don't want to find the span of W. You want something else that spans W. Or you can say find a spanning set for W. The way you said it first, or the way I was suggesting that you may say it, find the span of W, doesn't work. because the span of W means find all linear combinations of elements of W. But W is a subspace, so when you find linear combinations, you just get W back. You don't get anything new. The span of a subspace is actually the subspace itself. So never say find the span of W if you mean find a set that spans W or find a spanning set for W. Here's another related question. The set S has 1, 0, 0, 0, 1, 0, 0, 0, 1. And I might want to ask you, does S span W? And is this different than asking, is span of S equal to W? Are these two the same or different? Sometimes students say that span of S isn't W, span of S is R3, and that is correct, because from S you can actually get everything in R3, not just W, but everything. But then sometimes students say, but S does span W, because they're thinking, can I use elements of S to generate everything in W? And the answer is yes, you can do that. By combining elements of S, you can get everything, including elements of W. So maybe S does span W. The answer to that is no, because these questions in math are exactly the same question. Is span of S equal to W is the same question as does S span W. That's a little bit different from the way we might want to use the word span, like from an English point of view, but in the English language point of view. But these questions in math are exactly the same question, and the answer to both is no. The answer is no, because the span of S is R3 and not W. So S does not span W, S spans R3. Okay, I'm done with this lecture, and I will see you next time when we talk about linear independence.